Lorenzo is an associate professor of technical in Glasgow, and I think it's also 10 years ago, that's an anniversary, that you finished your PhD in the subject of type control. So it's actually one of the first PhD dissertations that was ever completed on a subject in airborne wind energy. So I think this is a great opportunity to see what happened since then and now. So please.
Thank you for the introduction, Roland. Good morning to everyone. It's a great pleasure to have the opportunity to give this talk. And for this, first of all, I would like to thank the organization for inviting me to give the plenary speech of today. Also, to be on the second day of the conference, I think is good because yesterday I could double check, hearing all the different presentations, whether the topics I chose a couple of months ago for my presentation are timely and relevant, and I believe that definitely they are. So yesterday, at some point there was a question, I think by Udo, to the panel, why it's taking so long from 1 minute or 1 hour of flight to complete operational autonomous systems, and that is linked to the first part you see in my title, Automation Challenges in Airborne Wind. So I will say something about that, about what are these challenges and whether there are actually some fundamental challenges or not there, so something really new, not just for this field, but for the whole automation, safe automation engineering area. And then there was a question from the audience, someone who asked, we are a university, the companies, what can we do in this space? What do you need, if anything, from us? And this is also a question that was puzzling me since now a few years. What is the role of academic research in this phase of airborne wind energy development? I will also comment and draw some considerations about that. I also start with my own historical note. It's funny because Roland started with 10 years of airborne wind, I guess because it's 10 years ago that you entered the field. Then Stefan Branek says 18 years of airborne wind. So for me it's 15 years almost of airborne wind. What happened in these past years? And actually there has been, as was said already yesterday, huge development, starting from people literally almost fighting barehanded with kites and primitive control boards, up to all the things that we see and hear in presentations today. So there was a lot of knowledge being built, models, understanding how the systems work, experimenting, building more and more sophisticated prototypes. So these 15 years might be, appear to be long time or short time, depending on the perspective. Definitely what I can say is that this is extremely complex technology, and in my opinion, 15 years to reach to the point where we are now, it's actually pretty fast, pretty quick development. And I will come back to that in a few minutes. What was the role of academia in all of this? So actually, it was a substantial contribution. I think all of us can argue that without academic research, we would not be here today. So first of all, in academic groups, we built prototypes and did first studies. So the very first prototypes were built with few exceptions, mainly in academia. And then this technology was transferred to startups. Here I mean not necessarily spin-offs, but also, or actually mainly, that's the most important part, transfer of people, of competencies. So these are examples of startups in which the people collaborated or worked in academic, other university or research centers before founding a company. And then also equivalently importantly, the academic circles, they did dissemination, had to foster the funding, and in general build the community. So examples are all the series of Airborne Wind Energy Conferences, two edited books, a lot of papers, and many funded projects with the joint presence of academia and companies. And now the question is, okay, now we are in a phase where clearly the companies are much more ahead than anything that can be done in academic circles and in academic university or research centers. So what can be the contribution now in this current phase? And I leave that for the end of the talk. So was this development in the last years good enough? Of course, we should define what is good. But I think definitely an accomplishment is to have raised the interest of governments, national governments, and also, I think more importantly, the European Commission, to look much more deeply into the field with an independent study. This was mentioned already by Roland yesterday. I know this study very well because I took a minor part in it as a technical consultant. The study on the challenges in the commercialization of airborne wind energy systems. So actually, if you read with attention this study, I think that some key points are there. So the first one, okay, I copied it, I'm quoting, but in short it says that with 1%, with the current knowledge we have, okay, so with the best of our current knowledge, what we know is that with 1% of inland use in Europe, we could supply more than 100% of the electricity need of Europe. If we use 15% of land use, then we can cover 18 times the electricity need or 3 times the total primary energy demand with airborne wind. And 1 to 15%, this range is because, of course, there is uncertainty in where actually you can exploit the sites or not, but it's already a lot of let's say areas were removed. So, of course, it's not saying 50% or 100% of the land, doesn't make sense. Is 1% a lot? Well, 1% of land use is the current use of land by conventional wind turbines in the Netherlands and Denmark. So it's not an impossible number, this 1% of land use. So this is recognized, and I think decision makers, after commissioning this study and getting this response, they cannot ignore it. And in fact, conclusion of the study is that the case is still uncertain, and I guess everyone here can agree that there is still uncertainty, but it is worth going further and explore the technology. And then what was proposed in this study is a risk-controlled approach. So stage gate approach with specific and well-defined targets to be accomplished in order to unlock further support. And crucial is the collaboration between private and public field. Okay, but also was the question yesterday, now wind and solar are very cheap, so is there still a case for airborne wind? And here actually I have a pretty clear opinion that this the funding in airborne wind will not stop for the reason I just said. It's potentially disruptive, potentially can contribute a lot to our energy mix. And on the other hand, there is a huge challenge we are facing. These are data from the International Energy Agency. What is shown here are the difference in carbon dioxide emission related to energy. Okay, 1 year with respect to the previous one. So you can see in 2015 and 2016 there was a slight increase, which is generally good. But then in 2017 there is an increase, and 2018 even higher increase with a historical high peak of carbon dioxide emissions for energy. And what is the reason for that? Well, essentially every government tries to achieve growth, and with our current energy mix, 80% based on fossil fuels, increase in GDP means increase in carbon dioxide emissions. I mean, there is no way around it right now. So the only way to decouple the two trends is actually to spend money. So we as societies should decide to invest our money to actually decouple these trends and achieve some growth, but at the same time improving the, let's say, reducing carbon dioxide emission. And the situation is even, let's say, more dramatic if we think about the future. So there is a prediction by 2040 of plus 90% power demand. So that's twice the global electricity generated today in 20 years. And in order to meet the sustainable development scenario, so to keep an increase of temperature below 2 degrees, 85% of twice the electricity generated today should come from renewables. So to me, it's pretty clear that right now, I mean, wind and solar can be cheap, but they just might be not enough. Okay? And so I think it won't stop the research and development in airborne wind until ultimately we either prove that it's convenient and doable, or ultimately we prove that it fails. Okay, but so I said this is actually mainly a societal and political challenge. But for me, when once societies will decide to invest and spend money to, let's say, deal with this problem, then all technical solutions should be there, including airborne wind. So this is why I think investment and support in airborne wind will continue. So how can we bring airborne wind to be a good alternative? We have to grow in credibility. And how to grow in credibility? You have to remove barriers. So this also comes from this study, AWEC study. This is essentially an overview of the different barriers, technical and non-technical barriers to the commercialization of airborne wind energy. So you have here a complete picture, and actually companies alone cannot deal with this complexity. There is really the need to collaborate among different stakeholders and between public and private. And now all these 15 years of development, in my opinion, actually were mainly focused just here, component readiness. So you see how much work still needs to be done. All right, so finally, the same study gives some very clear recommendations, and I agree totally with this. Prove continuous operation, so really reliability, autonomous operation, that's the very first one that emerged from the study, and the study involves also interviewing with stakeholders within and outside the sector. And then the other one is about resource assessment and complementarity. So is airborne wind a replacement for wind, or is it unlocking resources that conventional wind, for example, cannot reach? Anchor the learning, so build community, take stock of all the lessons learned, create a hub, testing sites, and very important, invest in enabling technologies. And this is linked to what I will say now in the second part of the talk about automation challenges. So invest in enabling technologies. And the mutual trust, so this trust that needs to be in place between public and private bodies in order to push further the technology. So I will focus mainly on this first point, but of course they are all equally important. So prove continuous operation. In our case, for airborne wind, this means safety, reliability, and ultimately automation. Actually, control engineering and automation engineering were born in order to have a safe, reliable operation of engineered systems so that the system behaves like it's expected to behave in our models. So the very use of automation is for that. And in airborne wind, this is special because automation is the real source of all the advantages of airborne wind, and at the same time or most of the critical parts. We all know that we have competitive advantage in principle because we don't need the structure, okay, cost. It's not useful to produce power, but that structure of wind turbine, the tower and the blade, that is extremely useful to stabilize the motion of the blade. So you just fix all the degrees of freedom except for rotor rotation, and then if the wind dies, who cares? The tower is there. That's not the same for airborne wind. And so far, what was achieved are hours or days of automated operation, which means that still there is someone supervising the system. And the goal is months or years of fully autonomous operation. So the difference between these two keywords is really crucial. Okay, but now let's look in the literature. What is a safe autonomous system? What are design guidelines? What are design principles? What are contributions in the literature about safe autonomous systems? So first of all, we have fail-safe system and fault-tolerant system. So in fail-safe system, essentially, the idea is that we design a system such that if there is a failure, the system can continue operating as it was doing before. And this implies usually high cost, proper engineering design, so FDA, FEA, as we heard yesterday in AWEC talk, and resilience to any single kind of failure. So triple redundancy of the sensors, dual or more actuators, so that if something fails, the system can still operate. Fault-tolerant control systems, and I mean, these are not exclusive. I mean, you can have, of course, fail-safe and fault-tolerant. Fault-tolerant systems are systems where there are algorithmic solutions in place to spot faults and to reconfigure the system to avoid that the faults propagate, and in this way preventing critical failure. And the system is allowed then to work in a degraded way. So these are some figures from papers in the literature. Every solution agrees on the fact that these should be hierarchical systems where you have actuators and sensors, maybe with their own local fault detection techniques, and then you have at higher levels sharing of information and more and more, let's say, high-level decisions about the system. So this is our solutions available as engineering methods in the literature. A difference arises when actually the system is working in an uncertain environment, and it is expected that this system can take decisions in full autonomy. And there again, there is literature, but actually these are much less established approaches. It is more really in research. And here, what is included is further hierarchical levels, where there are layers that essentially must provide faster reaction when something unexpected occurs, and then at the same time allow the higher up levels to take new decisions in autonomy. Okay, so to decide what to do in the face of something that was unexpected at the time of the design. Okay, now I think a sensible question is the following. In this, let's say, effort to have fully autonomous operation, is it all a matter of engineering design, or is there something fundamentally difficult and new and challenging? I think to answer, we need to look closer at the specific aspects of airborne wind. So it's a system that has to work in a remote and confined area with a harsh environment, low maintenance, it has to be economic. It's open loop unstable, so it needs control to stay airborne and to fly. Decisions have to be taken in short time if a fault happens, so it's time critical, and unsupervised. So up to now, I believe that if it were only because for these aspects, I think these challenges can be tackled with conventional safe engineering, engineering design of safe autonomous systems. But there are two aspects which I believe are really critical and makes a difference here. The first one is that we have different operating conditions and different. Next slide I will specify more, but there are substantially different operating conditions. And the second aspect is that the system relies on wind not only to generate power but also to stay airborne, so to be able to fly. And wind, of course, is an uncertain thing. So let me be a bit more specific. Operating condition, we have crossing flight, that's where we have a lot of control authority. The system operates under the main, let's say, conditions envisioned in the design. And there the design is designed for fatigue. Okay? So it's much more closer to design of conventional electrical and mechanical systems. So the cosmic light is actually not much of a problem. And then a very different phase is takeoff and landing. So here it's not, the relevant number is not really the number of hours spent there, but it's a number of takeoff and landing events, because each one of those events is with low, let's say, forward speed. There is much less control authority. The system is more, let's say, subject to uncertainties in the wind, in the waves, as we've seen yesterday. So each one of those events is a risk of a critical failure. Is this a minor part? Well, I was discussing yesterday with some people. So here it depends. Each one gave me a different number, but I was assuming, and I was thinking it's optimistic, that you have one takeoff and land every 2 days. Okay? Now you take a wind farm of 300 units of airborne wind energy systems. That makes 54,000 takeoff and landing events every year in the wind farm. So each one of these is a risk of a critical failure. And then someone say, okay, it's much less than that. Okay, let's say you have to take off and land every 10 days, once per system. It's still 11,000 takeoff and landing events every year. So this phase has to be absolutely proven against any fault, with extremely high probability you have to be able to do the takeoff and landing. And finally, the wind reliance aspect. The system, essentially, these systems will have to react to wind, which is not fully measured and is an uncertainty. And so the system has to make decisions in an uncertain environment. And the decision is, for example, whether to transition from crosswind to takeoff and land or back, and how to adjust the operation in each one of those two phases. And here I really think there is a fundamental challenge which is not, which is new and needs to be tackled. And the challenge is to ensure that this system makes a safe decision making, okay, with time constraints, considering all the possible system and subsystem faults, and using a partial information in this uncertain environment. So here the problem is that not only we can have a fault that disrupts the system, we also have the problem that if the system decides to transition in the wrong place at the wrong time, also can be a critical situation and disruptive failure. So, yes, that's what I said. And actually, we should not just think about crashing on sea or land. Even exceeding the load too much can bring to a failure in this case. Okay, but now when you have a new fundamental challenge, the first thing you do typically is to look at other fields, whether there are similar, conceptually similar challenges. And actually, nowadays there are many fields where people are looking how to solve similar challenges. Of course, with different specific features, but conceptually we are close to that. One is that comes to mind is autonomous driving. So you might be familiar with the levels of automated driving by the Society of Automotive Engineers. Level 5 full automation is where some years ago many companies were saying, okay, in 5 years we will have this autonomous cars. Now it's more maybe 15 or 20 years from now, because there is really fundamental challenging in how this autonomous system can handle uncertainty. And the other one is robotic system to do all sorts of, let's say, futuristic tasks, including exploring new planets. So, of course, it's very different. There are advantages and disadvantages with respect to airborne wind. These systems, they don't need anything uncertain to remain safe. They can just stop. Well, in our case, this is not the case. But on the other hand, of course, the complexity here is orders of magnitude greater than the complexity you have in an offshore wind field. But as again, conceptually, the challenges are somehow similar. And in these areas, actually, there are billions of funding for something that maybe will never be there. Okay, what are solution approaches to this challenge? Of course, it's a new challenge, so I don't have definite solution. Otherwise, I would have talked only about that in this plenary. So there is no established solution. And we can think about approaches, data-driven approaches, so-called machine learning. That's a lot of hype around it in these years. Of course, there are advantages and disadvantages. These are good methods at hard tasks, but in the literature, these are typically static tasks, image, speech recognition, these kind of things, not tasks with the time constraints and fast dynamics. And also here you need a lot of data, and there will be problems regarding how you certify your system, how you can interpret how the system works, how you can predict how the system will behave, and how can this be scaled or adapted. So actually, I'm not seeing this in this community, which I believe is a good sign. It's much more about model-based approaches, but also here there is problems because it's difficult to model the highly complex scenarios and to take into account all possible occurrences of situations that can be a problem a priori. So how to derive reaction logics in this plethora of possible dangerous situations, that's a challenge. And there might be something else, maybe something in between, maybe something completely new. And so here I come now close to the conclusions. These challenges can also become maybe opportunities. So if you think again at the autonomous vehicles case, there we have two factors. We have a societal challenge, that is the number of deaths due to car accidents, mainly because of human faults, and the business opportunity that car makers and other players are seeing, shifting from driver to passengers and the so-called passenger autonomy. So these two together are motivating huge research and billions of investment in autonomous vehicle technology. The case for Airborne Wind, well, clear societal challenge, need for energy security and mitigation of climate change. At the same time, business opportunity, plus 90% electricity generation in the next 20 years, 85% of that must come from renewables. So these two together should make good case for Airborne Wind. And actually, in both cases, we see that this automation and robotics aspects are really, let's say, right now, bottleneck and the main challenge. So maybe there is opportunity to reach out or somehow to link to research and development and the companies working on automation and autonomous systems. So this brings to the conclusion. I was saying before, and it was suggested also by this ECORIS study, that public-private collaboration is crucial for many things, regulations, funding schemes, and incentives. But of course, also academia, universities, and research centers, they are part of the public sphere. And I think really a crucial part of this public-private collaboration is the interaction between the companies and academia. As I said at the beginning, universities cannot compete. It doesn't make sense for a research group in academia now to develop from scratch a new prototype. But what makes sense is, for example, to provide expertise on specific aspects where research groups are really expert in, so really focused expertise on specific problems to the company. Work in R&D on non-standard problems. So, for example, this fundamental challenge in automation is really very important also, of course, for academic research, and solutions could be then transferred to the company. And then keep doing the good job in consolidating the results, disseminating the results, building the community, training the people, because actually this is also, when the companies get money, then they need to hire, and having people that are trained for the challenges in Airborne Wind is also crucial, of course, and continue to facilitate fundraising and research and development. And one good model that works, and works in other contexts with other, of course, industrial fields, is the joint research center model, where one or more companies get together with university to develop topics related to some area of common interest. And I will conclude by saying that now it's been, I think, 6-7 years that we consistently organize invited sessions at automatic control conferences on control of airborne wind energy systems. So we did the same for the next IFAC World Congress. The IFAC World Congress is the biggest conference in control. 3,000 to 4,000 attendees every 3 years. The next one is in Berlin, 2020. And there we have an open invited track on airborne wind energy systems. So if anyone has a contribution on modeling, control, identification, optimization of airborne wind energy system, please consider submitting. We also cover marine hydrokinetic systems there. And it's also possible to just send abstracts for presentation without the associated paper. The deadline for that is, everything is end of October this year. So with this I conclude. Thank you for the attention. And